let's continue. We can do it like on time. So we have different participants. These are like the main countries that are joining us today. So people from Peru, Brazil, Colombia, Spain, Mexico, Cuba, Ecuador, Venezuela, Uruguay. So please forgive me if your country is not there. I will do my best. Uh, Please complain in the coffee hour. I will update the slides. Okay. Uh, so we have put this like amazing program scheduled for today. So we are starting with the opening remarks until 8:50. So I guess we are great on time. So then we will have our first keynote speakers, Octavia. Thanks for like accepting our invitation. Then we will have the first block of oral presentations. So we have 3 oral presentations. We will have like 7 minutes per person, and then like following like a 3-minute question block. So it's a little bit different from like actual main CVPR conference, but I guess it will be great for like get to know like each one of the presentations best. After that, we have our first coffee break at 10:05 until 10:20. After what, we will have our second keynote, Arturo Deza from Peru. Arturo is not here yet? Not yet. Okay. I'm starting to sweat. Then we'll have our second oral blocks, sorry. So same strategy as the first one. So blocks of 10 minutes, 7 minutes for presentation, three minutes for questions. And then after that, we will have our lunch. So lunch will be served, depending if you choose sandwich or salad. So we will pick our lunch until 1. And then at 1 p.m., we will reconvene here for our third keynote. So third keynote will be Adriana Romero. So Adriana will join us for keynote number 3. Then we will have our general sponsors and mentoring hour. So this year is like a great mentoring team that has put together something like months ago. So we will have that discussion and sponsor hour at 3:45. After that, we will have our second coffee break, and then we will join with the poster session. So for poster session, it's great that it will be in this block as well, 4th floor. So we will have almost like 2 hours for posters. So it will be great to like discuss a little bit more our findings. And then after that, please be alert that after poster, we will reconvene here for the motivation talk. So it's like a new block, I will say, that we will have in this workshop. And we expect the best from that. So please join us after that. And then we will have the closing remarks of the workshop. So just be alert. It seems to be like a long day. Please drink and hydrate. It will be great to have you here. So this is a little bit more information about our keynote speakers. So Octavia Camps will start just in a minute. Adriana Romero with generative models as squareable world models, and then Arturo Deza as well on the quest of building the world's hardest benchmark of autonomous driving. So thanks for accepting our invitation, all keynote speakers. So just some self-promotion of people that have been working a lot of your free time, not too much, not too much free, but a lot of good efforts to put this workshop together. Of course, sponsored by LXAI. So we have Niels, Rodolfo, and myself. So Niels from Peru, Rodolfo from Cuba, myself from Colombia, working as operation and logistic chairs. Then we have also our starting program committee chairs, Will from Brazil, Juan from Mexico, and Andres Villa from Colombia. Thank you guys. You did an amazing job. Presentation chairs, so you guys working hard today. So Cisco, Francisco, and Jorge, thanks for accepting the invitation and your hard work as well. Then we have our PR team, excellent PR team, Ulises or Eduardo. How should I call you, Eduardo? And Daniela, who is not present, but she has done like a great job. Thank you, Daniela. You are hearing this. I will make sure to like thank you enough. Thank you, Daniela. And for the mentoring chairs, amazing team. We have Gilberto, from Mexico, Dustin from Ecuador, and Ivan from Mexico as well. So thank you guys. I know you have done a good effort with our undergrads. So I appreciate your hard work on this side of the workshop. Money, financial shares. Thank you guys. I know it's very stressful to play with money and try to, I mean, apart from all the inconveniences we had, it seems like we are here together today. So it's great to see you all. Thank you, Lydia, Ariana, Cisco, and Miguel. Like, it was a good headache, but I am happy to finally be here, and everything is going on right. So we are fine. Last but not least, Pedro and Jose. I should say, in every meeting, you were the last, but I need to apologize to everyone. Yeah, sorry about that. We try to shuffle who will talk first, but yeah, it's last but the best, guys. Thank you for your work, and all the volunteers that are here today. Thank you for your work, and let's hope for the best workshop today. Thank you, Pedro and Jose. Of course, we have our sponsors for today. So our platinum sponsor for this workshop is Google, and we have a set of bronze sponsors as well for our workshop. So Meta, Apple, Google DeepMind, DHO Research, DHO & Co, and 2 Sigma. So thank you for sponsorship. Thank you. So let's get started. I guess just perfect timing. There's any question? No?
Not yet.
Not yet. Okay, just prepare for Octavia. Okay, so let's start with Octavia. So first keynote speaker of the day. So Octavia received a Bachelor of Science degree in Computer Science and also in Electrical Engineering from Universidad de la República, Uruguay. A master's degree and PhD from Electrical Engineering as well, but from the University of Washington. So you are a local.
Yes.
So that's great. Since 2006, she has been a professor in the ECE department at Northeastern University. So you switch coasts. And 1991, from 1991 to 2006, she was a faculty at Penn State University, was a visiting researcher professor at Boston University as well in spring of 2013 and 2012. She was a visiting faculty at the California Institute of Technology and at the University of Southern California. So right now she's an associate editor of PAMI and a general chair of this year's CVPR. So her main research interests include the dynamic-based computer vision, machine learning, and image processing in representation for high-dimensional temporal sequences, which are compact, physically meaningful, and capture causality relationships. So let's welcome Octavia. I'm happy to have you here, Octavia.
All right, thank you very much. Can you hear me? Thank you so much for the invitation and for making this great program.
Yeah,
that's right. Yes, and it's also so nice to listen Spanish speaking in the conference. So and welcome to Seattle. It's my second home. I came to school here. So all right. So let's start. I changed the title a little bit because I wanted to talk a couple of things, and I think this is a better representative of what I want to talk. Which is order in data and architectures that can handle that. So architectures for sequences. So before I start talking about the content, I need to really acknowledge that this work is done by the students. I am the old professor that says, let's try this, and they say, no, that doesn't work, and then they come back and fix it. So this is work by Dan, Chusi, Yin-Chan, and Won, and also my ex-postdoc, he's now at San Diego working, and my colleague Marius Neuer. All right, so why sequences? The reason I care about sequences is because the world is dynamic and things happen in order. And of course, I'm a dog person, and I had to show a video of my puppy right there in the middle. But you all agree that video is very important in our lives and in this community as well, of course. The other thing is that you probably are familiar with the Johansson experiments, where if you look at this bunch of dogs, it's hard to make sense what they are. But the moment that they start playing in time, we can actually see patterns in the clouds of the dots that are moving. And also we can see clearly two people that are hugging and walking in those dots. So the temporal coherence brings a lot of information, not just the pixels. The other thing is, of course, the world is causal, right? So based on the past, we can predict the future. And that helps to make decisions every day, like how to cross a very busy street. Do I have time to reach the other side safely? So time, again, is important. So knowing that temporal coherence is important, that the world is causal, and of course, this also is very helpful to do self-supervised learning, we can do inference using these sequences. And in this case, these are generative models that allows us, for example, predicting the future, doing imputation. We have occlusion. Can I tell whether the green trajectory should be merged with the yellow trajectory or the blue or the red one? Does it continue walking in the same direction or is turning around? And we can also detect anomaly detections because we know trends and we know how the future is. And if we see something very different, then we know we have an anomaly. And of course, we can also do inference in a discriminative sense, for example, and I'm going to talk about that today, doing classification of actions. So not only generating, predicting, but also making classification. All right, so my talk is, as I said, I'm going to split it in two pieces. The first part, I'm going to be talking about the design of architectures that capture this temporal coherence in a way that make them very frugal, so you can use less data to train them. And also they're interpretable, so it means that it helps you to debug and change the architecture to address a particular problem that you might be interested. And the second part is something that we're presenting at CVPR on Friday, which is if you have data that should be ordered, but for some reason it got scrambled, can you reorder back? Okay. All right, so let's start first with the design of architectures that take into account temporal coherence. Okay, so here the main theme is that the input data are sequences that are uniformly sampled and they are ordered. So I do have the order, they were not scrambled. I might have missing data, that's totally okay. And examples of these, of course, are trajectories of points, dynamic textures, even the frames of a video. All of those are sequences that are ordered that way. Okay. All right. So, sequences is not new. We have been since the very beginning, and we have lots of architectures that work with sequences. So LSTMs, recursive neural network, transformers, of course. Okay. But these deep learning models typically are black boxes, and they take millions or billions of parameters to be trained. And they often are hard to understand and tweak. They are just black boxes. And so I think we have become used to having lots of data, and that's great. But in some applications, for example, in robotics, it's harder to get a lot of data. So you really want to have something that can be trained in a more efficient way. And I think also there's something, and I'm going to show an example that hopefully explains why I believe this is important, that if you understand what the network is doing, it's easier to tweak it and change it for different applications. Okay. So in my lab, we have been working for a long, long time, really, on trying to find deep learning models that are physically interpretable, so we can understand and modify them accordingly, that are rich enough to capture the complex dynamics of the world, but at the same time, they should be simple enough to be trained quickly and also run fast at inference time. And the less data I need to use, the better. So I want them to be frugal, to have only a few 100 or 1,000 parameters as opposed to millions and billions. So the goal is really having these black boxes that we are so used to these days and putting them a little window there that we can see what's inside and some knobs that I can tweak around to change the behavior of the network. Okay, so The intuition of what we do is that we're going to take these temporal sequences, but instead of representing themselves by the samples observations that we have, we're going to represent them by a dynamical system that created that signal. Okay, so I'm changing from the data, and my representation now is going to be the box that created that. And in the middle of that box, I have 3 letters, LTI. And for those of you that do not have control, that means linear time invariant system. So it's the simplest dynamical system that you can think of. Okay, and we can excite it either with an input, like I had before, let me say U of K, or some initial conditions. Okay, now you might say this is a very simple system, and I totally agree with it. But I also agree with this quote that says all models are wrong, but some are useful. So it turns out that in many cases, this is enough. Now, if this is too simple for you, we can make it more complex. We can have multiple linear time invariant systems, and we can also embed the data into a manifold where we can explain the dynamics using LTIs. And we can do that, of course, with neural networks. So we can have a neural network nonlinear in the beginning, map the data to a manifold where the dynamics are simple, and then go back to the original domain. Okay, so that's okay. All right, so now that I said I'm going to represent my data with these LTI systems, I just only changed language, but I didn't tell you how I represented this LTI system, right? So if you talk to your control colleagues, they would say, well, there are many representations that you can choose to represent this LTI system. Okay, and the simplest one is to just collect your data and have a sliding windows of your data and assemble that into a Hankel matrix, a matrix that has constant diagonals. And this matrix has nice properties that allows things, for example, prediction in the future. Now, but that's not the only one. Perhaps you are familiar with a state space representation. People that do tracking know about that, right? So you have a hidden state X that is linearly advancing time by this matrix A. You have an input U, and you have observations Y that is a linear transformation of the hidden state. And that's what we call state space. Or you can use a transfer function. Here's the Z transform, the ratio of the output. Sorry about this. Oh, no. Okay, thank you. All right. The transfer function, which is the ratio of the Z transform of the output with the Z transform of the input. And finally, autoregressive models where the measurement at time k is a linear combination of the previous n measurements. And all of these representations are totally equivalent. No one has more information than the other. But at some point, one might be more useful than the other. That's a different story. But you can go back and forth between all of them. Okay. All right. The thing is that these representations, except for just storing all your data in the Hankel matrix, they are frugal. They need only very few numbers to be described. Okay. And SysID is a field that actually learns how to estimate these parameters from the observations. So that's good for me because that means that my network will have to learn these few numbers if I manage to build that into my architecture. Okay. Another thing is that they are interpretable. Okay. For example, just take as an example the transfer function. Okay. So when you see here, can you see my mouse? Yes. What we have is a sum of factors, right? And so what that means is this is a linear superposition of simpler systems, each of them being first order or second order. By that, I mean it has only one pole on the complex plane or 2 poles. If it is a complex pole, you need to have the conjugate. So that's why you have second order. If it's a real pole, that's 1. Okay. So in each of these simple systems, depending where the poles are in the complex plane, they have these different behaviors. So again, I have a basis that I can understand what are the components. Do I have a constant component? Do I have an exponential decreasing component added to my system? Right. Here's another example in the autoregressive model. What we're saying is that the measurement of time k is a linear combination of the previous n measurements, which means that I need the memory of n to be able to predict the future. So again, that n has a physical meaning. If I want to predict the next frame, I at least have to have 3 or 4 frames, depending on the order of the dynamics. Okay. All right. So back in 2018, so several years ago, we used these ideas to design a architecture that we call Diane, and it was proposed to predict future frames in video. Okay, so the idea was that you have as input frames and the optical flow between the frames, and we have an architecture that had very few parameters, 160 parameters, not millions, not billions, 160 parameters. And that network learned how to produce a blue box, LTI, that produces these temporal signals. And once we have that, we use the previous frames as the initial condition for that system, and we could predict future frames. Okay, and it worked really nice. At the time, we were state of the art by actually an order of magnitude compared to what people were doing then. Okay, and it was a very simple architecture. Again, very few parameters to do. Okay. All right, so again, that's history. I'm pretty proud of this, I have to say. I like it. It's one of my favorite works. But so the properties of this is the architecture was frugal, only 160 parameters. It was interpretable because it uses the representations I mentioned earlier, and we're going to talk more about that. It's end-to-end, trainable with self-supervised data, is totally differentiable, so you can plug in into other architectures. It's generative, and it can generate not one frame, but multiple frames in one shot. And also makes available systems theory tools that can be used in that LTI blue box. So that brings with it a lot of extra. Limitation assumes linear time invariant dynamics, but as I mentioned earlier, that's something that's easy to fix by adding more systems and neural networks. All right, so let me explain now. This is a benefit of having a neural network that I understand what it's doing, what the latent variables mean, and allows me to debug and improve the performance of my system. So this particular problem is on cross-view action recognition. If you're not familiar with it, it is a problem where you want to recognize an action from a video. But the thing is that during training, you see videos from one perspective, from one camera viewpoint, but at inference time, you're seeing the data from a different viewpoint. Okay, so you need to transfer somehow your knowledge from one viewpoint to the other. All right, so in this case, I'm not doing generative, I'm doing discriminative. I need to classify sequences, I need to classify the apps. And I want to show with this example here that I have on the screen that this is a difficult task because the sequences can look very different in 2D when I change my viewpoint. So here I have the trajectory of the hand of a person doing an activity seen from two different viewpoints. And you can see that the green curves, they don't look alike, okay? And furthermore, if I have two different cameras looking, maybe they are not synchronized. I'm not starting to see the action exactly at the same time. So maybe in one case I have 5 measurements and the other one I have only 4. So that makes it the problem hard. Okay. All right. So again, my task is to classify these actions based on trajectories. But I said that instead of having the trajectories, what I'm going to have is these blue boxes. Okay, so I have translated now my problem. Instead of comparing the wheels, the trajectories, what I'm going to be comparing is the boxes that generated the trajectories. Okay, so that means I have to do classification of the systems rather than the sequences, right? And also in the process, I'm going to be doing this coupling between, I have a generative model, which is the blue box, and now I want to use this as a discriminative model to make the classification. All right, so here is my naive approach to the problem, right? I have this really nice tool that, as I said, I'm really proud of it. It's one of the best works I think I have done. And so let's apply it to this task. So what I did is, well, we have the video. Let's simplify this. Looking at the Johansson experiments makes sense to use skeletons rather than all the pixels. So take off the shelf open pose, build a video with the skeletons, use my Diane encoding and produce a system that will be able to predict future frames of this skeleton doing the action. But now, instead of doing prediction, what I'm going to do is feed the parameters of that system to a classifier. And the classifier will give me an action label. Okay. And this part is supervised. I have training data where I have the label of the action, picking an object or dropping an object on the floor in this case. All right, so we test that in one of the standards, actually many, but I'm going to show just one here, of the standards data set for this task computer vision, the NUCLA data set that has 10 actions performed by 10 different actors from 3 different viewpoints. And the protocol is that you train in 2 and you do inference on the third one. Okay, so we run this and we got 87.5%. Is that good? Well, I don't know. Let's look at the state of the art, right? And so back in 2020, the state of the art was 83.1%. Okay, so we are better than that. If we were 2020, we would be state of the art. But in 2023, somebody did something more smart and got 91.7. So we're kind of in the middle. Okay, now in my defense, this thing is just vanilla off the shelf. I'm not using anything about cross-view. These other papers are addressing the cross-view problem. And they use the full RGB, so they're not throwing any information. I only kept the skeleton. And they do things like render intermediate views to try to bridge the gap and use contrastive learning and all sorts of nice things. Okay, so I think we're not that bad. All right, but can we do better? And that's where the interpretability comes in. Okay, so let's look under the hood. What is my vanilla architecture doing? All right, so I started with the trajectories of the joints in 2D. So I have 2 coordinates per joint and across several frames. I passed that to my Diana encoder, which I haven't explained to you yet how it works. The Diana encoder, what it does is uses these atoms, first order and second order systems, okay, and have the response of those as columns of a dictionary. And the nice thing is that these columns have a structure. If you look at it, the first row has all ones, which is power 0. The second row has the pool power 1. The third row has the pool power 2, and so forth. So it's a structured dictionary. So you can put as many rows as you want, because if you know the first and second row, then you know how to complete the matrix as big as you want. So in the rows, we have time, and across columns are the different atoms, the different systems. Okay. And it's a very wide dictionary. That is, you have many more poles than input data. Okay. So now this Diane works as an autoencoder. So in the encoder, what we have, and that's why we have so very few parameters, is an optimization layer that what it does is express the input data in terms of this dictionary with as few columns as possible. So it will create a sparse set of features, this C over here, which is a solution of this optimization problem. The first term over here is simply saying, explain my data with a dictionary. It should be a linear combination of the columns of the dictionary. And you want that error to be as small as possible. The second term, what it means is, well, let's use as few columns as needed, right? Because dynamics tend to be simple. Let's not overfit the data. Okay. All right, so once you have these sparse features, right? And then, by the way, this optimization problem can be solved with off-the-shelf algorithms like FISTA, or it can be implemented actually as a neural network like LFISTA from John LeCun. Now, what I need is the decoder, and the decoder is even simpler. The decoder is only a multiplication that takes an extended dictionary, and remember, once I have the dictionary, I can grow more rows as needed, so I can add more time stamps in that, and multiply that with the sparse feature C, and that should be able to recover the input data, and if I have more rows, even predict in the future. Okay. And how we train this? Self-supervision, right? What we want is, we start with some random set of poles in the complex plane, and we measure the difference between the input data and the reconstruction or the prediction. And with that, we move the poles on the complex plane. So what we're learning here is the dictionary. That's the learn, okay? And it has less than 200 parameters. Each pole is just 2 parameters, magnitude and phase, okay? All right, so that's Diane. Okay, so that's what is in here. in my vanilla action classifier. Okay, so I dropped the decoder and just kept the encoder. I get these sparse features, and then I'm going to pass these sparse numbers to the classifier to give my action label. Okay, all right, so why didn't work as well as I was hoping? Okay, so let's look at this. So if my representation is good and the encoder did a good job, I would like that the input data Y should be equal to the product of this dictionary that I learned my network times these sparse features. Okay? That's the representation of the linear system that is creating these data. So this should be true. But now let's say I look this action from a different viewpoint, okay? And let's assume for now an affine camera, right? So that means I can multiply my observations by a matrix. And so if I multiply both sides of this equation by this matrix, obviously now what happens is that my coefficients cannot be the same. They have changed. It's obvious that these coefficients C are not invariant to rotations or scaling and so forth. So asking my classifier to be able to do a good job when I totally change my viewpoint is not fair. Okay. All right, so that's where the interpretability comes in. How can I fix this? Well, I can fix this because I know the meaning of this block here. I know where they are. Okay. And so let's look at invariance. Okay? I'm very old, and when I started in computer vision, we were really worried about the fact that we needed to do recognition no matter what. And we didn't have a ton of training data like we have today. Okay, so we wanted to find what was the essence. So the sunflowers are the same as sunflowers, the ones on the front and the ones on the back, then bigger and smaller, but they're still sunflower. A dog is a dog no matter the pose they have. And these two images of this hotel in Las Vegas is the same hotel, even though I'm looking from different viewpoints and different illumination, different time of the day. So that's invariant to all these changes. And a lot of smart people spend a lot of time and wrote books and papers on trying to find geometric ways of finding what does not change, even though when I change my viewpoint. Okay, and that was used as a cue for recognition. Okay, then in 2012, AlexNet happened, ImageNet was there, and we sort of abandoned this idea of invariance, and we hope that our training data is so big that we will see all of these variations, and the network will learn from that. And if we don't have that, well, we put it, right? We do data augmentation to try to cover that. Okay. All right. In time domain, what's invariant is a little murky, but I hope you can agree with me that if I'm swinging these two videos, for example, on the bottom of a person doing an action, and they look very different, but it is the same person is performing the same action. And the mechanical system, which is your bones, muscles, does not change. So that's invariant, that's intrinsic. And that's what I need to recognize. Okay. So I'm not going to go over the math details, but all of these representations for linear systems, they have things that are invariant to these linear changes. And so here I'm listing the poles are invariant, the dimension of the matrix A is invariant, the eigenvalues of the matrix A are invariant, the rank of the coefficients of the autoregressive model are invariant, and the rank of the Hankel matrix are invariant. Okay, so all of these things do not change. Okay. All right, so let's go back to this architecture. The problem was that these features over here do change when I change viewpoint. Okay, and so the classifier has a hard time doing that. All right, so but what we know is that this product, what it's really doing is, because C is sparse, is selecting which columns on my dictionary need to be used to explain my input data, right? And the poles of the system are invariant. So what that means is that the places where the C features are not zero is invariant. The color, which represents the magnitude of that coefficient, that changes. But the location where I had to paint something that's not black is not changing. Okay, so that means that I need to grab those locations and use them as my features. okay? And that's very easy to do. Basically, you have to learn how to threshold that. Okay, so we added this Gamble softmax layer that takes the C features and binarize them. And then we use those features to the classifier, right? Maybe with enough training data, my classifier before would have learned that really what it matters is that was non-zero, but it would have taken a lot longer to do this. I know what architecture is doing. I can go and make this a small change, okay? And now let's see what's the effect, okay? So remember, these are the previous numbers I showed. 87.5 was the vanilla with no thresholding. Just by adding this layer, I was able to increase performance by 9%. And now we are state of the art. Okay, so just by understanding, okay, what the features were and modifying accordingly. And I think that's the benefit of this approach. All right, so we were throwing away the RGB pixels. If you add them back with a separate layer, there's nothing really innovative in that part. You actually boost performance all the way to 99.4%. So, okay. And the next thing also is that the dynamic bar is really agnostic of the fact that I'm using 2D skeletons. I can use also 3D skeletons. It's just I have more columns on my input data. And if you use 3D, we get basically 100%, 99.9%. All right. Any questions? I'm about to finish the first part. Yes.
How long is the sequence of the skeletons that you're using?
So for train the input,
Yeah.
it's about. I have to ask my student, but I think it's 30 frames or something like that.
Can this use like representing the action that the person is doing in the video?
Yes.
Okay.
Yes. Yes. Yeah. Yes.
On the context information representation, like
Yes.
together, it's just CNN, like a
I3D basically. Yeah. Yeah. We just and we do a contrastive learning a little bit to boost it because we don't have any kind of invariance.
Yeah.
Yes, sure.
Sorry. You put the coefficient directly to the network, or you do the Laplacian or something?
No, I put it directly to so the classifier is a network, it's a bunch of MLPs.
Okay.
Yes.
And you constrain something about the dictionary, or?
No, the dictionary is just a structure, and we initialize with the poles to be within the unit circle.
Okay.
Okay. Only 5 minutes? Okay. All right. So, oh, no. This is the most important slide today. How do I stop it? Yeah, I have questions in a minute, so that's not fair. Yeah. Okay. All right. So let me try this again. That.
You can use 10 and then 5 more minutes.
Thank you. All right. So this is the second part. So now the idea is kind of the opposite. I know time and ordering is important, but somehow my data got scrambled, and I give you a scenario why that might make sense. And I want to use the fact that I know that the data should have been ordered to put that order back. Okay, and so this is a poster on Friday in the morning. Okay. All right, so here's the scenario I'm thinking. There's a soccer match. There's a lot of people in the audience. They all took, pictures, videos, upload them to the web. And now what I want to do is collect all this asynchronously data and create a movie out of it. So I want to order them in time. So now I can, integrate multiple recordings. And they can be also for medical purposes or even weather and other things where you have distributed capturing data that's not necessarily synchronized and you want to put it together. This is also very similar to the problem of image puzzles. You have a bunch of pieces, they have been scrambled, some of them might be missing, and now you want to rearrange them in a formal picture. Okay, so how do we do that? The intuition is very simple. We want to recover the ordering, and for that we're going to use a diffusion generative model where we want to generate the positional encoding of the frames or the pieces. And this is conditioned on the actual data that you have available. And some of them might be missing, but the ones that you have, that condition how to rearrange. So makes sense that this is first or this should be the last. That's based on that. All right, so see the pipeline for training. We start with a set of pieces. In this case, it's complete. We have the positional encoding. Then we shuffle them. Then we randomly select some of them to be missing. And we are going to do diffusion on the positional encoding and the missing pieces. And we're going to use the other pieces as conditioning for the diffusion model. Okay, so we protect that together in flattened patches. We apply reverse diffusion, and we recover the ordering of the whole set of pieces, and the missing pieces get inpainted, basically, and then we can rearrange. So at inference time, you give me a bunch of pieces and some missing ones that are initialized with noise. Okay, we apply the reverse diffusion transformer layers to those, and we recover and reordering, and we recover the missing pieces in painting, and then together with the given pieces and the ordering, we can assemble the figure again. And here are some, they're kind of tiny, I apologize, but you can see here on the puzzles of images. So the first column is a jigsaw, that's all mixed. The second column is reordered, but not in painting the missing pieces. And the third one is within painting, and the last one is the original ground truth. And on the second half of this, what we have is that the pieces are actually missing boundaries. We have gaps, and we still can do it. But this is about sequences in time, and so we did that also with video. So you have here in the input, we have a scrambled video where the frames have been shuffling order, and some frames are missing. And in the middle, you see our recovery video. So you see the smooth trajectories. It looks natural, and it looks very similar to the actual ground truth. Okay, so take-home messages. 33 minutes, so not too bad. Sparse dynamics-based representations like the ones I showed earlier in the beginning of the talk are nice because they are compact, they're easy to interpret and explain, and it can be put into end-to-end design. So we did that for video prediction, and now we're doing it for cross-action recognition. They provide explainability and editing capabilities, as I just showed. The fact that we use invariance by design, I also think is important. Again, we have become now spoiled. We have lots of data, but yesterday I was at a workshop where we're talking about recording every second of your life so you can predict. And obviously you cannot handle that much data. So trying to compress things using this type of frugal models, I think is important. And in robotics applications, for example, it's hard to actually collect all that data. So the nice thing about this is that Dynamics provides ways of learning invariance by design and putting that into your architecture rather than trying to just learn it from the data and hoping that the network learns that. It simplifies the models, as I was saying. And I'm repeating myself, reduces the amount of data and type that I need to train. For example, for the cross view, I can train with one viewpoint and I can recognize from the other viewpoint. I don't need to have data from both. Because they're really what they're using is a temporal ordering can be applied to different modalities, not just video. So anything that is ordered can be applied. Okay. And now for the last piece of the talk, well, this was a problem where we were trying to go from a set that is a jumble of frames, pieces of an image, and order them in a place. So it's set to sequences. And what we see there is that the ordering of the data is a very strong prior that allows you to recover the ordering back. And so I think really the message is temporal coherence, spatial coherence is a very important cue that should be used when it's available. With that, thank you.
Thank you, Octavia. So please take a question.
Yes.
In some workshops, talk about equivariance
Yes,
Which is actually different.
it's the opposite of invariance, yes.
Why you don't talk about this case about equivariance instead of?
So in fact, actually, I didn't explicitly mention, it's on the slide for the second application. We are using here a transformer, especially because it's equivariance, right? So transformers are agnostic about the ordering of the data, and that's actually why you put in the positional encoding, so the transformer doesn't, you doesn't get pulled for that. So depending on the setup, equivariance is a good thing. So here I'm using it actually, but in other cases, I prefer the invariance, so something that, it does not change across different viewpoints, scaling, or other changes. It depends on what you are after or what's your application. Yes.
What else?
Well,
George? Yes, please.
Sorry.
You
Sorry.
have plenty of time, so please feel free to ask.
I am curious because usually you need to learn the dictionary learning and the sparse coefficient.
So the sparse coefficients are the output of is the features at inference time.
Yeah.
So let me go back to the slides. So I can see.
But usually you say that need to be sparse. You
Yes.
try to impose during the training.
Yes, so during training and inference.
Because you say that you use FISTA, but FISTA, you need to fix the dictionary, right?
Right. So
It's only for the inference? Or?
no, let me see if I can go. To the training here, yeah. Okay, so let's hide this if I can. All right, so the way you train is you initialize your dictionary with some random points, okay? So this box here, the encoder, runs FISTA with that dictionary. That will produce a set of sparse features because that's what FISTA does. It sparsifies the solution of that objective function that I have. I use the output of this FISTA and I multiply it with my current dictionary to do a prediction. And now I compare my prediction with my input. If the prediction is not right, I use a gradient to go back and change the pulse location and run FISTA again, okay? And I keep doing that, okay? And FISTA is differentiable, that's what's nice, okay? So this layer is an optimization layer, but it can be, I can pass through my gradients. And so I can change the pulse. So that's training time. At inference time, now the poles are fixed, okay? But at running time, I will have to run FISTA here, okay?
You run FISTA in each iteration of the training?
In each iteration of the training, I had to run FISTA, so that makes it a little more expensive, okay? But because these matrices are small, it's not that terrible, okay? And then at inference time, I also need to run FISTA. And as I said, we use FISTA because it's convenient, but you can also, and I like the fact that I have very few parameters, but you can use LFISTA, which is a network that will increase the number of parameters of architecture, but not by much. And then you can just do it just basically by propagating through the network.
Thank you.
Yes.
I have a question about the second part.
Yes.
I recently saw a paper that is like combining the Mascowton encoders with diffusion models to reconstruct the missing patches. How is this different for that? I guess it's just about the order because
it's about the order. Yeah. So it does both things. So it paints, all right, but also it doesn't know where they go to have the ordering together. Okay, and so that is what makes different. And many years ago, we did have, before deep learning, we addressed this problem, and we used tools very similar to the ones that we're using in Diane, where we were using the dynamics, and we were able to actually recover the ordering by imposing that the dynamics explaining the data was the lowest order possible. Okay, and we were very happy with that, and we wanted to do now this problem with missing data. And I really like explainability, so I really wanted to do it the other way. We couldn't, okay? And so that's why we went to diffusion. And now we can do both. We can learn the encoding of the position and the inpainting.
Is the encoder learning like better features that use doing the normal Mass-Calc encoded with diffusion?
That's what we hope. We haven't, this is very fresh. We are working on that. We are hoping not so much for the images, but
For videos.
for video it's going to be much more important because the thing is in the ordering we really are focusing on how you put things together, right? But not so much about the object type or thing. So I don't think we will beat mask diffusion models for learning features for object recognition. But I think for video, it could be good. And another application I didn't mention besides the crowd sequencing is, for example, if you have low temporal resolution videos and you want to do high res time, right? So you can infill, and it doesn't have to be, again, equally spaced. So you can have slower and faster and slower, and you can fit in with this approach. And we have it for that. We know it works. Yes.
Do any error analysis to see where the system breaks down and why? So for example, is it because of the number of holes?
Yes. Yeah. We
Corner?
No, yes. So one of the things that I didn't put much emphasis in my talk, I kind of hide it, is that the main assumption for invariance is that my transformation has to be affine, okay? It cannot be perspective, okay? So if I have a strong perspective distortion, it's going to break down because the math doesn't hold anymore, okay? Now, the action recognitions, they do have, one of the viewpoints have quite a bit of distortion. And that particular viewpoint performs worse than the others. But we can fix that a little bit doing contrastive learning at the end as well. So, but yes, that's one of the things that we look at.
Time for a last question.
I think, yeah.
Yes, about this last question.
Yes.
Did you try with another kind of geometry in order to avoid this thing? Maybe to include another transformation like this deformation?
So the thing is, the main thing I'm using, the main tool is linear dynamical systems. And so that's why linear goes well with linear, right? So when I do a linear combination of things, it still things hold true. And I can do affine by a simple trick that I use homogeneous coordinates. So I augment one dimension, I lift it up, and now I'm linear again. If I go to perspective, that is harder. We started looking at there are some things that we can still do. And the thing is, the math becomes more complicated. And so, yes, the answer is yes, but I don't have anything to show.
Thank you.
Thank you.
Let's thank Octavio again.
Thank
so
you.
much. So now we have the first block of oral presentations. So oral one.
Yeah. Claire?
David Cathy.
Va para arriba, ¿no? Muéstrale la. Sí, pero yo creo que no. Lo hago con esto, porque no está funcionando bien. Está funcionando bien. Sí, es es al contrario. Ya. Yo lo estaba probando y no funcionaba. Claro, tiene un punto si quieren.
We notified you with this, yeah?
Pero es al contrario, ¿no? Para explicarle que eso. Claro, yo también estaba. Ya, si quieres usarlo para la. Si quieres usar el pointer, puedes hacer un. ¿Necesitas ver la pantalla? Sí, ponlo para acá. Cuidado.
Okay, I can put here.
Sí, o si quieres.
No,
Tienes que
okay. No, because sometimes we have that.
Let me to present.
That's right.
Hello, everyone. It's a pleasure for me to start the first oral blocks. Today we have 6 in total. The first 3 are in this skill. Let me introduce to Professor Clever from Brazil. Thank you so much to be here.
Hello, everyone. Thank you for having me here. And after Professor Octavio, there is no way you have my more interesting approach. But as I'm presenting like a sequence classification, you can pretend it's she, giving like a very interesting explanation. Well, I'm Kleber Zanquitin. I'm professor at Federal University of Brazil, and today with my colleagues David Castro and Bayer Bezerra, I will present an approach for handwrite recognition. And we are specifically dealing with hard constraint for application of this problem. And offline handwrite recognition is a classical approach for pattern recognition. The idea here is try to extract text from images. And I know we have like a lot of good models doing that, but normally they struggle when they have hardware restriction, because we need like very big models to work with. And this is still an important approach, even with the digital transformation we have, specifically for personal notes, official documents, and archives. And this kind of restrictions is still a problem on that. And if we look back, when we have a lot of improvements, we start from recognizing numbers and digits, words, and then we go from segment lines. And right now we are able to extract all the information of a document without any kind of segmentation and doing even the layout transcription. And to do that, we are using very big models like recurrent convolutional neural networks, or specifically transform-based models that can like make a transcription of the information without any kind of segmentation, using a single frame to do that. But the problem is those kind of attention operations they do is they are very complex in both time and space, and then they are normally quadratic. And then we have like more complex image, and specifically to deal with handwriting, we need a lot of resource to do that, and we are trying to improve this kind of problem. And to improve the performance, we start from the state-of-the-art models and try to understand why they spend more time and resource to doing the work. And we are proposing a new approach, considering encoder decoder approach. The encoder part, we are using reducing the space, like the spatial recurrence of the information. We are using convolution, octave convolution, to reduce the information we can deal. They use a kind of feature maps in a lower resolution to deal with the recurrent information. And then in the code part, we are dealing with flash attention and multi-head attention to have a more speed process of extract information. And the key features of our approach are using octave convolution. This is a multi-scale strategy to use a lower version of the information, try to not using all the information to process. And then after that, use a gated convolution, which is a special way of spatial attention. Then we are able to focus in specific parts of documents. This is important when you are doing the layout extraction. And after that, in the decoding part, we are using a kind of memory efficient attention and flash attention for specifically extract information, and not using so much resources specifically for memory and GPUs. And to experiment with, we try to use a very hard data set. We are using historical documents because normally they are big, and the system we have right now, there's no good results on that. And we have two tasks in experiments. We have a single page when the one specific model, single model, try to recognize the whole page, the structure and the text, and the double page when we have two pages in a single image, and the model needs to understand the layout of the information and organize information during the extraction. In the single page document results, we have very good resolution and dancers, the model we are proposing here. We also use another constraint. We have the denser max, where two models normally use 48 gigabytes of GPUs to work. And then we are trying to reduce this amount of information because we are trying to do this kind of process in the edge. I know 12 gigabytes is still a lot, but we are going in the direction to reduce this. And even when we are using only 12 gigabytes against 48, we have like 3 times more samples processed. We also have a peak of processing the GPU on 3.5 gigabytes, where the other state-of-art models have 9, like 6% of reduction, where it's interesting. And we also are able to deliver more throughput. The amount of information we can process in the same time and with the same resource can be increased by 30%. When we are dealing with 2-page documents, as they are bigger and we need more memory to process that, we still have very good results considering this. We have the best results in recognition and even in the throughput. We are in a good position. It's not still the same with denser because we have restrictions of memory, but we can deliver the best results considering faster than with the state of art right now to do this approach. And when we are considering different metrics to evaluate the performance of the model, when we consider like GPU consumption versus training, when we can like reduce the use of the GPU during training, then we can even put more information during the training. We have the best results in this trade-off. When we evaluate the throughput to training, that means we can like put more bags or more memory during the training to increase the use or maximizing the use of the GPU. We still have the best results. This is important because normally we need a lot of information to have good results in this kind of application. And also, if we consider the memory scalability, and as we increase the number of lines of tests we're recognizing, our approach is better to have the results considering the other approach. And even for the latency inference, we have better results as we are increasing the batch size. Our model have better results delivery, and the other approaches are increasing the use of resources. And just a final remarks, we believe this model could be like a baseline for approaches in this field because we are going to user approach, trying to process in the edge. And I think this is very potential, specifically when we are trying to bridge the information we have to the transformer, the digital transformation, and the information we still have in documents, specifically in archives. Thank you very much for that.
Thank you. We have time for a couple of questions. Then what? Questions?
Yes, thank you.
In the data set, you have multiple pages.
Yes.
And so did you segment the data individually?
No. The model needs to do that. Like you have a book, like an open book, and then it needs to understand the layout of the information and extract in the correct order, and just using a single model to do that in one task. Yeah, you can have that, but normally in this specific data set, they are high resolution information because they are like historical data when they do in the libraries. It's about like one image is like 5 megabytes.
Maybe I missed this, but at some point you had said something about recurrence being used very popular 5 or 6 years ago. Do you still think that recurrence, maybe I missed this, is it still being used in what you're presenting today?
No, actually, we start with that. Right now, it's all transfer-based models. Yeah. And then this is a problem because normally the attention process is quadratic, and then on time and space, and then we are focused specifically on this here.
Thank you so much. If you have more questions, you can find in the post session in the afternoon.
Thank you very much.
Thank you, Claire.
Esto se con speaker. Es la voz activa. Es muy práctico. No, es fine. Y ahora descargando la auto también. Esta joda así.
Then we will continue with the next presentation. It's a pleasure for me to present one of my grand friends, Ivan Reyes from Guadalajara. Welcome, Ivan.
Thank you. Good morning, everyone. My name is Ivan Reyes. I'm a PhD student, and today we're gonna talk about our recent work about robustness for image classification through adversarial sampling with a method that we're proposing that is called delta data augmentation. So this is the agenda I will be working on. And as an introduction, it is well known that deep neural networks are susceptible to adversarial and natural image alterations. Some of the most popular examples of this is the image of the left. It's an image that if you put some altered pixels in terms of the white or black, the image classification model that is related to this type of signs will be outputting some different, like a max limit for velocity. So this can lead to incorrect confidence predictions of an image classification model, and this is a very rough topic to deal. So speaking about robustness in general terms, given a input x and a function f of x, we are trying to keep the model performance in the same for each one of the x prime of the neighborhood of an x, given a distant function called delta with a maximum limit of delta. So in terms of robustness for deep learning and computer vision, this is a very common example of a panda, which we are trying to preserve the model performance under adversarial or naturally induced image corruptions. And here we are seeing a panda that the model is trying to tell us with a 57 confidence. And if we add some noise, some adversarial noise here, we are seeing the same image for eyes, but the model is going to give us a different classification with a more confidence of this. So basically we have the three types of robustness. The adversarial examples is the type of robustness that we are doing here in this paper. Well, but we have some other image corruptions, which is changes in the brightness or the darkness of an image. Also, we're having shiftings into the training and testing set. So for this is a common example of the pigs that with deep learning, we can make pigs fly. So this is a hypothesis of our work. What if we could extract some of the robustness from an already adversarial robust model? What we are trying here is to put some of the knowledge of a robust model to train a downstream task for classification. So this is our proposal, which is called delta data augmentation. And basically, we are trying to fetch some model A that is already pre-trained and is already robust. Let's say we are training this model in an ImageNet, a very large data set. And we are trying to apply some adversarial attack, let's say PGD. The PGD stands for projected gradient descent, and we are trying to query this model to obtain some of the deltas that were useful to treat the model. So once we have these deltas, we are using these deltas as transformations when we are trying to deal with a downstream task, let's say with a data set B, for example, C410. And we will keep trying to incorporate these perturbations that were useful for a larger data set into this new novel data set, and using this as a matter of data augmentation for training a robust model B. So with this, we are avoiding to train for adversarial training to reduce the performance in terms of GPUs. And we are trying to incorporate and to reduce the gap between the normal accuracy and the robust accuracy. So for our experiment configurations, we are dealing with a Model E, which is a wide ResNet 50, which is one of the top 10 robust bench models for having natural and adversarial robustness. So for this model, we are applying a PGD with ImageNet, and we are fetching and grabbing some of the perturbations that was most useful for attacking this model. And these perturbations are incorporating in terms of data augmentation, let's say here for a CPAR10 as a manner of data augmentation. And we are using ResNet 18 pre-trained on ImageNet for our Model B. And basically, we are testing the model in terms of the L2 norm and L infinity norm in these epsilon intensities. So for the datasets, we are dealing with CPAR10, CPAR100, HBHN, and the MNIST and the fashion MNIST. With these datasets, we are trying to prove that our model is sufficient good for dealing with RGB images and grayscale images. And in order to compare our method, we are dealing with some of the most popular data augmentation methods, which is the rand augment, out mix, no data augmentation at all, and of course our method. So these are some results using the ResNet 18 with the L2 normal RGB images. We can see that our method for data augmentation, this is the red line, is outperforming in most of the cases of the epsilon intensities. Also, if we change the norm for an infinity norm, we are also seeing that our method is working well with the data set that is called HBHN. If we increase the size of the network in terms of the layers of the ResNet, we are using here the ResNet 50, also on RGB images, also for the dataset HBHN and the L2 norm and the L infinity norm, we are having here some outperforming performance for our method. So as a conclusion, we are here dealing with the first method for data augmentation without using of adversarial training. And we compare some of the analysis of the most used methods for data augmentation in terms of robustness. In terms of future directions for this work will be to increase the range of the robust pre-trained models. So thank you. There's some references. My name is Ivan, so thank you.
Thank you, Ivan. We have time for a couple of questions. After this.
One question. So at a high level, what is the main difference between what you're proposing and straight up adversarial training?
Okay, with adversarial training, you're having like an overfitting for the method that you're dealing with the robust attack. Also, you're having more inference and more training consumption in terms of the model. So if you're using these corruptions in terms of that augmentation, you're basically running very fast in terms of the training, and you're not having this overfitting for the specific type of attack and data set.
So, sorry, this is a naive question. I'm not super familiar with this space, but when you're comparing sort of your data augmentation method with others, so are you controlling for sort of the amount of extra data that you're adding? So are you adding extra data, or are you just perturbing the training?
Yeah, that's a very good question. We are adding more data in our terms of data augmentation. We're using the basic training set and also the corrupted data set with the perturbations in the same manner of the other data augmentation techniques, to be fair.
Got it. And how much are you adding?
It's the double of the size of the training set.
Thank you. One question more, Ulises?
Yes, maybe I missed something.
Yes.
What are your metrics about robustness? I only see the performance decrease with accuracy, but how do you measure actually the robustness?
Okay, yeah. In the state of the art, the most used metric for measuring accuracy is the measuring robustness is accuracy under some of the epsilon intensity attacks, which means which is the performance under these adversarial attacks. I mean, we could, in the paper, we can see some of other metrics, the natural accuracy, which is only seen here is the adversarial accuracy. But this is why, if you go to the top papers about robustness, every single one is using just accuracy under adversarial attacks.
Yeah, okay. Thank you. If you have more questions regarding with this work, you can look at Ivan in the session poster. Thank you, Ivan.
This?
No.
Okay. So let you know when you have to meet. Déjame escondo esto porque va a ser mal un poco.
Thank you, everyone. For our last oral for this blog, we have Maria Luisa Lima from Brazil. Thank you, Maria Luisa.
Hi. So this is STGate, leveraging spatial temporal convolutions for gate-based emotion recognition on videos. So first, let's talk about emotion recognition. So emotion is a really big part of human communication and social understanding. I think we all can relate to like having a talk with someone and looking at them and inferring what they're feeling based on maybe the way they're talking, the tone of their voice, or their facial expression, the way they're holding themselves. And we react accordingly. We try to inflict or change the way we're behaving so that we can affect someone. So if they're feeling bad, we can try to make them feel better. So a lot of this communication can come from verbal cues, which mean someone can tell you what they're feeling, but also from nonverbal cues like facial expression, body language, and gait, which is the way someone walks. And previous research has already suggested that the way someone walks or the gait contains social markers, and also Rother in 2009 has already successfully used gait as a nonverbal cue for the emotion recognition tests. So we can leverage gait for this task. And why is it interesting to use gait? So when you try to infer to recognize emotion using things like facial expression, or using some other devices, you can actually change the way someone is behaving or expressing themselves. So you're interfering in the data that you're collecting. So by using gait, you can just put a camera somewhere, and the person, the user, is allowed to freely walk. So you're not interfering as much as you could otherwise. And you can use it in some applications like healthcare analysis. For example, because interment patients, they can struggle with mental health issues in interment, and by collecting this data, you could allow healthcare professionals to more quickly react to the way, to the struggles of the patients. You can also use it in smart cities or, for example, urbanism applications where you have this parks, streets where people may be feeling insecure or angry, and you can actually interfere and do and change the way people are relating to the city. So there are some really interesting applications where you can use gait. So how do we do this? So gait is the way someone walks. So you can imagine it as a sequence of skeletons. So you have graphs, right? The data shape, there are graphs. So you have the skeleton of the person in the spatial area, and you have the temporal edges, meaning the temporal sequence of the skeleton through time. And you can use spatial temporal graph convolutional networks to process this type of data. And we used STGCN++ as a backbone for our work because it has some mutable kernels for the temporal aspect of the convolutions, and it has some optimized processing of the spatial edges. So this is our proposed architecture, STGate++. So we extract the skeleton inputs. Maybe we have body pose extractor from video, a live feed or something like that, and we extract the skeletons and input it into the network, and then we get the inferred emotion. We trained this on the eGate dataset, which is a state-of-the-art dataset, and it has 4 emotions: happy, angry, neutral, and sad. So what did we achieve with this? So we got state-of-the-art performance. We got 87.5% accuracy. At the time we were writing this, the Humane work wasn't out yet, so we were comparing to STEP, which was the state-of-the-art at the time, with the 83% accuracy. We also converged faster during training. And this is interesting because when you have lower computational resources, you actually need to train and do experiments, and this allows you to do them faster, try more things. So we were able to converge faster as well. So again, we improved the state-of-the-art by almost 5% in accuracy. And in comparison with STEP, the state-of-the-art, we also required 72% less apex for convergence. And we were able to also improve the performance on ambiguous scenarios. In psychology literature, there are some emotions that are harder to distinguish among themselves, and we were able to perform better in happy and neutral emotions than STEP. So just to bring some discussion to our reality in Latin America. So it's hard to find data, it's hard to find good quality data, and for specific tasks such as emotion recognition through GATE. And there are very little data sets, and they're not suited to Latin American reality. So GATE, for example, is very centered on Europe and North America. So because emotion expression is also linked to culture, it's possible to infer that this application wouldn't work well in our reality if we were to use it in Pacific, where I'm from, or some other place in Latin America. So I just wanted to bring this to attention, since we're having this crowd here from Latin America, that we as researchers could focus more on building good quality data sets that are focused on our area. So in conclusion, we used GATE for emotion recognition. We obtained a better performance than state-of-the-art by improving the architecture. And we also got important insights about the lack of data, the difficulty of data availability, especially for our scenarios. We want to bring applications closer to us, so this is the way we should go. But that's it. Thank you.
Very much, Maria Luisa. We have time for a couple of questions. Jose?
Have you tried to include like, I don't know, some kind of metadata? Like, for example, I don't know, I can think of something that is really trendy today that include like descriptions of what the person is doing, like, oh, this person is walking very fast or something like that. Because you are just considering like the geometry of the person. I mean, it's just like a graph of the key points. So
yeah, there's actually something called effective features that are extracted as well, but we're not using some other metadata.
Okay.
Just these effective features.
Yeah, so I'll say I really appreciate the part. I mean, first of all, great talk, but also I really appreciate the part at the end talking about. I was going to ask about some cultural differences and things like that, and did this kind of work. But so if you have more thoughts on that, I would love to hear more thoughts. But I also have a concrete technical question as well about them. You said it's 72% fewer epochs, but I was wondering in terms of like computational time per epoch or sort of additional complexity or anything like that. Is there any kind of like is 72% fewer epochs? Is that an accurate reflection of the actual training time?
Yeah, during training time, it is actually very much faster in seconds. But during the runtime, during inference, it's actually longer. We have on the paper a table for that. You can look it up. So during inference, it does take longer, but during training, it's much faster.
Okay. We'll have maybe one question more. If not, thank you so much, Maria Luisa. Thank you everyone to participate in this first block of the workshop. Let me give you some advices. For all the attendees, it is time to the coffee break. You can take the coffee break in the 4th floor in that direction. And you can pass to the back for your LXI kit for this conference. Thank you, everyone.
Yeah, go and take your swap. There's like
There are some candies on the back, so please take.
There
it
is
back.
sweets, there is things.
Ryan, you
Please.
Good. Bueno. Muy bien, muy bien.
For the people that listen to streaming, we will take a break. We return in a couple of minutes. 15 minutes. Thank you.
Work.
Okay. And this is well, this small icon. Maybe uy, ¿se podrá mover? Okay, okay. So I'm representing Artificio, where I'm the co-founder and CEO, and Utec, where I'm a professor in Peru. I'm also going to be in the discussion panel, so later in the afternoon. So if there's any questions, that don't get answered or asked today, right now, I can always answer them later. Most of the work that I'm going to be talking about today is relevant to what we've been doing at Artificio, so I also thought I'd give everyone a hands up. So where are self-driving cars today? And this talk is going to be half technical, half not technical, more inspirational, I hope, than technical. But I think all of us are really aware that self-driving cars somewhat exist. They can drive to a certain degree. This is a Tesla driving autonomously in a city in the US, I'm not sure where. And you can even buy one. Maybe someone here owns one as well. And I think 10 years ago, no one would have expected that self-driving cars would be commercially available, even though FSD still has its somewhat of its flaws. And here's some examples that maybe are not so well known, but errors that Teslas make. So here on the right, you can see how a Tesla confuses its carriage with a person or a trailer, and now it rotated 180 degrees, and now it's a person and a truck, so it's morphed into another object. And of course, the car hasn't crashed, but this is still very bizarre. And on the left, you see here an example of the car, the Tesla, identifying stoplights, semáforos, right? But they're not really where they're supposed to be because it's another vehicle that's moving. So this is not really an error, but it's a bizarre natural adversarial example. So I think the other point that I want to make here is, even though the engineering part of a self-driving car has been really groundbreaking, there's still some interesting cases and flaws that maybe most of the people here in this room are still also aware of what's been going on with, not to put shade on any company, but Cruise and Waymo, where in this case, Waymo is like blocked a fire truck and it doesn't have the semantic information that a fire truck should break the rules because there's an emergency. And in this other case at Cruise, and this is happening in San Francisco, you can deactivate a Cruise car by putting a cone, like a party cone on the car. So I don't know if anyone has seen this, but this is more on the social side of self-driving cars, where San Francisco, despite being a very innovative city, is very against self-driving cars. That's really strange. You would imagine that they'd embrace it, but they're having a lot of issues with just the general population. Maybe not the scientists, although some don't fully agree with self-driving cars are trying to stop progress in this field. Of course, a human would know what to do in these cases. And in terms of the economic value, for those who aren't aware of the reality, because you go to CVPR and everyone's saying, we just raised 300 million or $500 million or 100 million or 50 million for my startup. Not mine, but other companies. Full disclosure. We have raised some money, but not that much. The reality is most of these companies are either went bankrupt or about to go bankrupt. In fact, without naming any names, yesterday there was a workshop in one of the autonomous driving companies, and the company that was supposed to host the session went bankrupt last year. So this is there's really a problem, that there's a disconnect that I also thought I'd share. That sure, there's a lot of really good R&D happening, but in terms of what is a product that many of these companies are selling or making money out of, it's not well clear of what the plan of profitability is. So if you have an R&D lab as a non-for-profit, you can raise a bunch of money from grant agencies, but if you're actually running a business, you have to think about how you're going to make money. So now going a bit more into how do we solve autonomous driving? I don't know. So who thinks maybe as doing an informal vote that autonomous driving is solved? So who would say, okay, so no one, everyone thinks that autonomous driving is not solved? Yes, so raise your hand if you think it's not solved. So who thinks that in 5 years we're going to solve autonomous driving, for example? Nobody. Okay, who thinks in 10 years? Okay, who thinks in 30 years? And then, okay, so more than half say never, I guess. So who thinks never? Okay, that's interesting, 2-3 people. So for those who say never, for example, what would be your definition of what is solving autonomous driving? Like, what would you be happy with saying, you know, I see this and it's solved, I would take a Waymo car or whatnot?
Anything that can happen on the road will happen, and we can
Okay.
control that.
Okay. But a human presumably can't do the same thing, right? So how would you compare that standard tentatively? As a human still makes mistakes. Oh, it's just something to think about, right? And maybe for your case as well, I think you said, you know, it's never gonna happen, self-driving cars. Where's your position? Is it similar take or?
I think it will happen in like a general environment. I mean, you
Okay.
cannot deploy autonomous car to every place in the world. It will happen in some places.
Okay.
For sure. But for some places, it will be really difficult.
Really difficult. Okay. Would you think in the US it's gonna happen the next 30
I would
years, for
say that
example?
probably for developed countries, that will be a reality in some
Okay.
point. But for example, for some places in Latin America, maybe, I don't know, some places in Africa, in Asia, would be difficult.
Okay, so I'm gonna try to argue the opposite, that's where we really want to solve the problem instead of the US or Europe or Asia. Not that I hate on these places, I'm a secondary, in spirit, American citizen, as they say. So, okay, so this is, I'm gonna start off by talking about, how most of these systems see. This is very, very basic, okay? So my main focus is just vision in this talk, so this is gonna be very, very basic, and then I'm gonna start going into more details, but the simplified self-driving car pipeline is perception, doesn't say here, but what do I see? Navigation, where am I going? And control, which is what action do I take? And there's most of the time, these three blocks are either put in a serial way or in a parallel way, and each one of these blocks has its own problems and complications, right? Sometimes knowing what decision to make is extremely complicated, even if you have perfect information. Sometimes knowing how to get there is also extremely complicated because you want to be efficient and save gas. And sometimes perceiving is also really difficult. So again, each one of these blocks in this pipeline is a complicated problem per se. And there's a lot of arguments about training a system end to end, but in a very simplified way, this is self-driving in a nutshell. So for those who have not been going to CVPR, so presumably everyone here has been before, the current state of affairs in terms of real-time object detection and semantic segmentation and pose estimation is extremely advanced, right? You could do this with near perfect accuracy in real time. This is the Tectron 2. This is not something developed by us. This is an open source model that 10 years ago you would have said, oh, this is impossible, right? You would need a supercomputer to train it, which they did, in fact. But it runs pretty fast on a computer with a regular GPU on a laptop. So inference is relatively cheap, and it does it in a very precise way, even at the pixel level. So if you were someone like Elon Musk, you'd say, oh, yeah, you just saw your self-driving car company or Tesla, and which is probably what he did, right? When he saw something like this. And because it's very exciting, right? You wouldn't have expected to see something like this 10 years ago, and the state of the art in computer vision is extremely advanced. However, as we already saw in previous talks, there's things like such as adversarial examples and out of distribution objects that I'm also going to be talking about in a bit. But the primer of, and these are some slides that I borrowed for a non-scientific audience, just to make things extremely simple, but so I'm sure this is redundant for many of you, but this is how generally the training pipeline goes for a CNN or any deep learning system where you have a data set, for example, of people and pedestrians. You define your loss, your architecture, your optimizer, and you tell the system to know what a pedestrian is. You would do the same for a car, for example. And ideally, at testing, if everything works right, you should be able to draw some sort of hyperplane for classification between defining and discriminating between what is a car and what a pedestrian, and so forth with a lot of classes, not just two, right? Of course, the real world is extremely more complicated. And I think this cartoon illustrates that point, where there's not just in LATAM, but in the real world, there's stuff like a Cybertruck that doesn't really look like a car. In Peru, we have the heladeros, right? It's not really a motorized vehicle, but it could maybe act as a motorized one. There's handicapped people that have to cross the street. Places like India and also in Peru, there's a lot of informal commerce, where if you don't see an image like this one in training, you may not know what to do in deployment. And if you remember the example that I showed about the Tesla, seeing the carriage in the street in some maybe more rural side of the US, it's pretty much what happened, right? There was no accident, but when accidents do happen, it's because they've encountered visual information that they don't know how to process most of the time, okay? So how do you solve for these type of bizarre out of distribution objects? And that's really the question that as a company we're trying to address, and hopefully in that direction we can help solve the self-driving car crisis. So the errors, right? And how do most of these systems are usually deployed and trained? You need a lot of data, clean data most of the time, not out of distribution. A supercomputer to train this, and usually it's gonna cost you anywhere between, for a company like Tesla, $1 to $6 billion, I believe, a year to train a system to do full FSD, which is extremely expensive. And as a huge parenthesis, I think that now everyone is very enthusiastic about the whole scale is all you need, right? Give me all the data, give me all the GPUs, give me all the money, I'll melt the glaciers, who cares? And somehow I'm gonna get a really high score on the paper or to tell my customers that I'm doing a great job. And I think that's extremely inefficient because as humans, you can just maybe eat an apple in the morning and perceive the whole scene for the next 12 hours without any problem, right? So that's also something to think about as well. And at testing, sure, you would still need most with OEM companies have smaller GPUs or devices in which you can do inference, again, on IID data, ideally from which it's been trained, which is, so here's an example of data we've been collecting in Peru, and this is running an open source model that thought that was a train. That's not a train. Here's another example. This is not a train, right? So this is just getting Meta's Detectron 2, running it on data that we've been just driving around different cities, both urban and rural in Peru. This is not a truck, this is a sign, right? So you'd be surprised that these systems without any sort of fine tuning can make these type of mistakes. Sure, and just to play the video one more time, in defense of many of these open source models for self-driving car companies are not open source, by the way, but we're trying to get there, is it is getting some other objects right? Bus, pedestrians, people, so it is getting those right. Car with high confidence, but then this bizarre case like truck 87, it doesn't really make sense. You can kind of see why it's somewhat it's a reasonable mistake, but it's. And now in lieu of reminiscing the earlier talk today by one of the students, I believe Ivan mentioned this about the adversarial images. This is still happening today, and this is an example, old school, from about 10 years ago, from some students at MIT that 3D printed an adversarial turtle, and the computer thinks this is a rifle, and it's not a rifle, no matter how you see it. If you do, let me know, we're in an experiment, but no matter how you see it for the general population, it's not a rifle, but the machine is, as Quintana Ronaldo would say, who's playing it, it is multiple. It is a rifle when it's not, right? And I was just speaking to Olga outside about the pros and cons about doing research in adversarial images, and I'm going to get back to this at the end of the talk. So what is an interesting opportunity for Latin America and places like Peru, for example? There's a lot of chaotic driving in Peru. This is not something I'm necessarily proud of, but there's bad drivers, there's bad pedestrians. We're ranked #2 in the world with the worst drivers as of TomTom. This is a car going in reverse in the street. Like, you do this in the US, you go to jail, or in Europe probably, you get your license revoked. So I'm really curious to see how in simulation, most of the current self-driving car companies that are operating either in the UK, in Europe, in Asia, or the US would react to this type of data. And I think here's where there's a lot of value to say, let's try to stress test most of the current models. Again, this is just an open source one that's not for self-driving, but for the ones that are, how would they perceive and interact and make a decision in these sort of environments? So getting data from, I don't know if someone here is from Thailand, but from Peru, for example, or Lebanon or Thailand would be like the naturally occurring adversarial examples where you really want to push the boundary of stress testing how a model would work on. And potentially you could do two things with this. You could train a model on this data, right? Or you could stress test a model that hasn't been trained on this data to see how it would behave or see. So this is a bit what we're proposing in terms of the strategy of the company, which is, let's not melt the glaciers and raise $500 million. Let's try to raise something less, like 50. Not just kidding. I'd say something like 3, something more reasonable, something more nuanced. And I'm also surprised why some of these companies raise too much money. But let's really focus not on the GPU and the processing power, and let's focus on the richness of the data to see how we can take advantage of that in general to be more efficient and at the level of representation, build something that's more robust. So that at testing, we could use a device that is also relatively cheap, that would also fit in a self-driving car and would also know how to respond to both in distribution and out of distribution objects. So so what is a solution that, again, as a company we're pursuing, and it's really training and testing on a diverse data set that you may not see in places mainly developing nations. So we've been collecting some data from Peru, Lima, Cajamarca, and Cusco, both the capital and other states, the departamentos in the country, like Cajamarca and Cusco. There's a variety of the data in terms of the data set distribution, in terms of whether you see buildings. So Lima is more gray, where there's more taller buildings, and places like Cajamarca and Cusco, which are more rural and they're open. And this is just data we've been collecting in terms of having drivers with a dash cam go around the city and collect data and then see what we this, right? And in this case, we've just been projecting certain frames from the data set into a 2D plot. This is just standard t-SNE on top of an embedding. The reality as well of most of the problems that current self-driving car companies have in the developed world is, how do they know what an obstacle is? They sometimes call it debris. And there's obstacles that you do want to avoid. For example, this is a piece of wood and a brick or dirt, or this banner that fell off the street. And there's obstacles that you don't want to avoid and you just want to go straight over them, right, in terms of safety. There's also the distinction that is very subtle between motorized and non-motorized vehicles. And this is important in terms of knowing how you should react in terms of the speed and location of objects in a scene. So if an object is motorized, you want to be more cautious in terms of how it's going to react to a decision you may take. And this is a tuk-tuk in Peru, mototaxi. They're really common in the developing nation, in Peru, Colombia, Brazil, pretty sure all Latin America. Also in Eastern Asia, they call it tuk-tuk in Indonesia, for example. And informal commerce is also very popular in Latin America, like el heladero, right? Like, what class should you give to an heladero, right? Or someone who sells elote? Is it a pedestrian? No. Is it a tricycle? No. Is it a bike? No. Is it a motorcycle? No. Should you even create a new class, right, for people who do informal commerce, right? So we can even joke about this, but it's a serious question, right? Because some of these cars are being sold. Teslas are being sold in El Salvador, in Chile, and I believe in Mexico, there's a production facility. And they will encounter these type of situations with these type of visual stimuli, right? And they need to know how they have to react to prevent an accident. And not just Latam, the United States, this happens in the real world too. So maybe anyone can, I think it's easier in the left image. What's the bizarre situation? The upside down sign, right, for pedestrian. And in the right, I don't know if anyone has seen this stoplight before. Does anyone know who's seen this type of stoplight for the first time, for example? Okay, so a lot of people. So for those who have seen it for the first time, do you know what it means? And you can make an educated guess. So I think as far as I know, and it's a white line, it's just a white vertical line. It's priority access to the bus. And I think specifically it signals the bus whether it should go straight or it should just stop, okay? I believe, I'm not really sure if that's the case, but because I saw this in Boston a month ago and I was also really surprised and I had to Google this. So, but it's, you would not see this in South America. So again, for better or for worse, sure, training on out of distribution scenes from outside developing nations could be useful, but there are other cases where maybe not so, right? Because these type of traffic signs you may not see in places like Peru, Colombia, Chile, or Brazil. So what the company really has to do with, in terms of what we're thinking about product, is benchmarking as a service. So let's get access to APIs or open source versions of, these are computer vision models, but self-driving perception models. And let's run this on the data that we're collecting from developed worlds such as Peru, and this is data from Lima, from Cusco. This is more of a qualitative assessment, but we'd have to also run numbers to see the accuracy, the number of false positive rates for pedestrian, car, motorcycle, and whatnot. and expand this not just for Lima, but for LATAM. Ideally, it should be the whole world, but start with the emerging economies because most people think there's no value there. And what we're trying to argue and hope is that the value is in this type of distributions because seen these images so often, right? And if you maybe train and test your system on these images, you can get more added value. And we're building, this is a prototype. This is not real data. I don't want anyone to say Tesla's #1, like they're not, okay? So, but this is the vision that I have for what we're trying to build, where I'm sure everyone has seen leaderboards for LLMs where you can see OpenAI #1, then Mistral, and it's almost like US versus France versus then Russia and Japan and all the startups from all the world that have their own LLM, models and foundation models. So we're trying to do the same thing, and we want to openly do this audit as well for something as critical as the self-driving car market, because if you make a mistake in an LLM, you predict the wrong word, nobody dies, right? In a self-driving car, you take the wrong turn and bad things could happen. So this is easier said than done because of regulatory policy. So in reality, it's not as easy to, Wave or Waymo and tell them, hey, can you give me access to your API? They're going to be like, no, like, why would I do that? And most of their models are also closed source and they have their own IP that they don't want to share with anyone. But it's a starting point, and it's what we envision in a certain way. So how are we collecting this data? Because right now we just have, which is not much, 500 videos. The plan is to get to about 60 million every 6 months with the new round of funding we're raising and the partners that we have, which is there's a lot of transportation and logistic companies that want, because of security, to record a lot of the driving information when they're transporting food or money from point A to point B. Think of, for example, Rappi motorcycle drivers, right? In LATAM, if on the helmet you could give them a camera, and also taxi drivers too that are more independent workers, and we would pay them, and we're thinking about a payment plan where we paid them so that they can collect data for us at a rate that they're also happy with, because there is a global recession, whether no one likes to talk about it or not, and everyone's trying to find different ways to make money. So for someone who is doing taxing, if they can get paid $1 per hour of data, which maybe in the US doesn't sound like a lot, but in places like Peru, Mexico, Brazil, Argentina, maybe it's a bit more, they would gladly do it. And this is something we're thinking about as well, where they send us the videos over WhatsApp, for example, through their phone. And it's okay if the data in their phone is, from the camera, sorry, is not as high resolution as an actual dash cam, because you do want to have the variety of the sensor data when you want to do both training and inference. So that's actually a good thing. Sometimes we had investors tell us, but why would you want someone to get data from a phone? I'm like, well, it's cheaper, it's zero friction, and it gives more diversity to the data set. And the third stage of the plan, which is again what we're also doing, is as we keep collecting this data, we upload it to the platform so that maybe someone can buy and sell data as well. And the data commercialization part, thinking just purely in terms of business, hasn't really been explored, because most data sets are open source in general for research, which I think is great. But maybe there's a possibility to buy and sell data. Like suppose you have this data set for, I don't know, butterflies in the Amazon that someone else really wants to have. You can have an open source version, and you can also have maybe a paid version, so that even if you're at a university and it's not for profit, you can get some sort of income to finance your project if you license your data. So again, that's nothing to do with self-driving, but it's something that we're thinking about too. So some other announcements, because I realize I only have 5 more minutes left, is for those who are interested in this type of direction, there's a workshop we're hosting at ECCV that's called ROAM, for Robust Auto Distribution and Multimodal Models for Autonomous Driving. And the emphasis here is to stress test models with data from places like LATAM and Eastern Asia and Eastern Europe, where no one is really going to collect these data sets. So this is a Twitter handle for those who like to use Twitter, ROAM ECCV 2024. We're looking for people who can submit papers, who want to review. If someone who wants to talk and give one of the keynotes about this subject and is working on this, please also let us know. We're trying to make it in person. So you'd have to fly to Milan, Italy, and we'll try to find a way maybe to fly you out there too. But this is also an exciting partnership between the university, something that's not for profit, and the startup that is for profit. So I think there's opportunity in general for what we're doing there. And something that we really want to stress test, going back to part and the earlier talks, is there are cases where classifiers can correctly know that this is a banana, and these are these other adversarial patches in the real world that you can print it's a toaster. You can kind of make sense on why it thinks it's a toaster, but it's really not one. And we want to do the thing for self-driving, and we've been trying to download as many. This is again not a self-driving car. This is just not even a car. This is driving around, printing an actual adversarial quote unquote image and seeing how a system like, and it's actually a bit disappointing. Here I have to, it should say failed. This is a failed adversarial test. But this is so you have an idea of what we're doing. Like, we really want to make the system think that this is a car or a person when it's clearly not, okay? If someone, by the way, is doing research in adversarial objects, do please let us know, because we really want to, most of the models that we're doing this, testing this on. This is a simulated example, so not an actual printed one, but one of Donant, one of the co-founders in the company, generated this adversarial image that is supposed to confuse the surrounding class for it to not think it's a pedestrian, a car, or any other object. So if it's on top of the car, it should make the system think it's not a car anymore, but it still works. So the adversarial attack is failed in this sense too, but we really want to push the envelope to make it, in this case, product plant is not really one. Think that this is a person, for example, when it's really not. Okay, so again, these are failed tests, but it's things that we're thinking about doing in the actual physical world. Okay, and this is not going crazy and just putting a bunch of images and saying, okay, let's really make sure the Tectron and YOLO fails, but they actually still do a pretty good job. So this was kind of a bit disappointing, because when you see adversarial research papers, you can always see how the system makes a mistake, but when you put it in the real world or run it through another model, it's not cross transferable. So it's something. So just to wrap things up, there's we have our first baby steps are of our own, like, foundation model is a word I don't like to use, but I've been seeing everyone use this, because it's like, everyone uses self-driving. Oh, we raised $200 million foundation model. All right, here's the money, right? So take this with a grain of salt. It's not really a foundation model. We don't have whatever billions of or millions of dollars of funding or images, but we're trying to do the opposite, right? Foundation model with fewer GPUs, little amount of data, and let's see what we can get. Okay, so this was a one-man, as they say in Transformers, a one-man effort, mainly done by William Berrios. He actually gave a talk, I think, at LXAI at NeurIPS 2 years ago about the model we developed, where the question we're trying to answer is, are transformer models good models of the human visual cortex? So we want to create an in silico model of the visual cortex, so how a human actually processes visual images, and put that in the next generation of self-driving car models. Okay, so there was this competition called the Brain Score competition that MIT hosted about 2 years ago, where you declare your own computer vision model, a transformer, CNN, anything, and you're going to cross-reference the representations of the model with actual neurophysiological data recorded from a monkey. Okay, from a monkey when it sees the same images. So ideally, if you have a model that sees like a monkey, which a monkey has similar representations than a human, these correlation scores should be 1. Okay, so you're not just predicting banana, banana, human, human, monkey, monkey, cat, cat, but the internal representations in the network should be matched with actual neural physiology. And in the interest of time, this is a model that we work with William. So we used a regular cross VAT, did some adversarial training as well, and we put in rotational invariance. So we used a pre-existing model and fine-tuned in a particular way. And the long story short is that William got like 3rd out of 200 people, and he was just working on this by himself. Well, I was just the coach, but he was from his mom's basement, did this, and there were other people, like Fancy Labs from MIT, and and Europe. And this was pretty amazing because we also broke a record for modeling area V4 in the visual cortex. So I know we're almost on time. So aside from the number, and this is the cortex model that we have, and the record we broke, I want to show the qualitative impact of this model, okay? So in this model, instead of, when you do an adversarial attack, instead of just seeing noise, you can see how the class warps into the object that you want to fool the system in. So essentially, the adversarial images of the machine are adversarial in a way for the human as well. And this is what we really want to push for because it gives a higher degree of explainability. And there's this metric called brain score that allows you to do this. And this is just another example. So, you know, for the same different images, different classes, you know, cat becomes hypercat, becomes dog, insect, or whatnot. And the same for the other classes. And these are just other, there's a paper that William and I wrote about this, Berrios and Deza, and you can read it. But in the interest of time, I mainly just close with what you can do with this. You can try to do similarity search for bizarre unknown objects. And I think this can also potentially help when you're deploying a new emerging economies. So these are just other plans we're working on, scale from 1,000 videos to 1 million, right? With putting an adversarial loss and a self-supervised constraint. The conclusion, what are the opportunities Latin America can play in a self-driving car revolution is stress test state-of-the-art computer vision models, maybe create new foundational models on other distribution data, commercialization of data. We're thinking about selling data that we're collecting in Peru, for example, to companies like Wave, Tesla, Waymo, and Cruise, so they can test their models in-house. And there's a lot of new space for regulation because in these economies, there are no self-driving cars, so you can actually, you know, set what the rules are, which is interesting. So just to wrap things up, there was an article that we wrote about 6 months ago that went viral, and the press thought we were like this multi-million-dollar company based in the United States that's deploying self-driving cars in Peru, and it's really just a team of 4 of us. You just need a small team of really talented and motivated people. So really, it's Victor, Lunant, and David that deserve all the credit in this, and I'm just, you know, providing them high-level guidance. And you know, startup world has its ups and downs, but I really want to stress test that this is a team effort, and even with a small team that shares the same vision, you can accomplish a lot of super cool things. In this case, creating value for LATAM as well. So that's pretty much it. And we're always looking for collaborators. So if you guys want to work with us, partner with us, fund us, you know, just feel free to send me an email. Yeah, that's pretty much it. Thank you for having me here.
Maybe we have time for 2 questions. Any questions? Yes.
Hello. So we have been working for a while now with understanding how these types of classifications, but also miss rate can impact the autonomous vehicles and semi-autonomous vehicles in Brazil. And one of the things that we are basing our research in is a very straightforward paper from the people at Leeds. And they were looking at how these object detectors, looking at pedestrians, they can misclassify or not classify people based on gender, race, etc. And one of the results that, for example, a child is less likely to be detected than an adult. So we are starting our research in this track, and based here on your talk, I just wanted to ask, what do you think are maybe the things that are more important that these models do not detect today, but they need to be detected in order to have at least some level of other systems working well in South America?
Yeah, so I think the example of kids is really relevant because in places like LATAM, kids are more unconstrained to play on the streets, right? So there is a danger of running over a child in a place like LATAM versus in the US. I think parents are definitely more cautious. So that's one thing. So you definitely do want to reduce the false negative rate for that, right? Saying that there isn't a child when there is one. I had a discussion with Victor, with everyone in the team, but Victor was very pushy about this, which was when we had a meeting and said, what should the car do if it sees a stray dog? And stray dogs are very common in LATAM, in the emerging continent. even in very rich neighborhoods. So what should a self-driving car do? And that answer is, he was very bullish on don't run the dog over, and I think that's what you want to do, right? But what are the other possibilities, right? Is there another person around? Like, you want to, of course, minimize any sort of human casualty. So, but these are cases that do self-driving car systems in the US have dog detectors? Like, I don't know really. And so that's something to have in mind too. Sure, they're not people, but you don't want to just run over a dog because it's not a person, right? It's still a living being. There's another interesting case of objects that you do want to run over. This sounds a bit debatable, okay? But something like a plastic bag. If you have a system that is doing just computer vision and misclassifies the bag for a person or another bizarre object like a ball that really doesn't, or that has mass but really doesn't, then the car is just going to do an abrupt stop. And this sometimes happens in the highways. And when you have assisted driving systems, I've known people who've told me that a plastic bag, places, certain parts in Peru are actually very dirty. So, the wind can throw a bag around and the car will just do a stop, but it should have just kept going through, right? And it'll put the driver in a hazardous condition. So I think it really depends on the location, but these are the type of questions we're thinking about too. And to what point should these be their own classes as well, right? Should there be a new class called obstacle, right? Or debris, where it's a super class of other secondary classes that we should know whether we should stop or keep going. So yeah, I don't know if I answered your question, but yeah, okay, but it's a good one, yeah.
Thank you. One more question.
Yes.
So have you looked at other modalities as well? Like, I don't know, LiDAR or infrared, that how they compare with, first world country data sets like that?
Yeah, that's a great question. So we were in the process of raising money, the next round of funding, to get LiDAR sensors to start doing these comparisons. I really don't know. So but I think it's really exciting. The reason why we're really going strong with vision is because vision is easily scalable in terms of a business side of thing, right? You just need a phone, a dash cam. You can even buy companies' cameras and tell them, pay me $30 a month and this is your insurance. And just cost $30, and the camera maybe costs not more than 50 or 100, but LiDAR sensors are at least $5,000, right? So that's where things get a bit complicated. But it's something we're thinking about doing. I also don't know how in the future companies are going to value LiDAR versus just pure vision-based systems. But I do think, as much as I'm a fan of computer vision, given my background, and I really don't know nothing about LiDAR, that I think you still will need systems that have LiDAR and radar and ultrasound to have sensory redundancy reduction across all modalities, right? And I don't know who's seen what Wave has been doing, but they've been doing some interesting stuff too, where they're trying to use now like LLM models to tell the self-driving car what to do based on language, as if it was like this co-pilot agent. So testing those systems on this data, I think, would be interesting. Yeah. Okay, thank you. Thank you, David.
One last announcement. Probably we're going to take a group picture before the break, before the lunch. So please.
Hacemos el cambio del. Otra. El siguiente bloque.
¿Es? ¿No?
No.
Ahí estamos dándole. Hablamos. Sí. Si yo me cuadro esto.
Okay, thank you so much to be here. We will continue with the second oral block presentation. To start this oral block, I want to present Luis Schreiner.
Actually, I'm the second author.
Okay, Gillian. Gillian. Sorry, thank you. Welcome.
Good morning. It's Guilherme Chardon. Don't worry. I get it. Yes. Thank you very much. I'm going to present our work. We've been developing for a very long time, actually. It's a high resolution detection of Earth structural heterogeneities from seismic amplitudes using convolutional neural networks with attention layers. Okay. Basically, this work, I don't know, I'm going to talk more about the problem because I'm not sure how familiar most of you are with petroleum engineer. I'm not, so I worked with in this project. I worked with brilliant petroleum engineers and they did most of the geophysical part, but they tried to make me understand the problem and it helped when solving it. So when I ask you, how do you imagine an oil reservoir looks like? I believe that most people, like myself included, about around 6 years ago, would imagine just a big pool of oil underground, and then extracting it is just like digging and doing like digging a well, like inserting a straw and just sucking it up, right? That's a fair assumption. You wouldn't be wrong. So wrong. Actually, the oil reservoir is more like, at first it's not just oil, it's mixed with sand, brine, water, gas pockets, which can be deadly if you don't know about them, and a lot of things. And it's not really concentrated in a big pool. It's more like a network of tunnels that are the geological faults and fractures under the earth due to seismic activity. So to extract the oil from these places, for instance, we need to first map these areas using seismic sensors and sound cannons. And afterwards, we need to have a lot of people with geophysical backgrounds to map this area, find the interesting places where there might be oil and there might not be oil anywhere, and to start planning on how to dig those wells to start extracting the oil and the gas and whatever is mixed in there, okay? So that takes a lot of time, a lot of money. Think about billions upon billions of dollars for one reservoir. Okay, so if you do a wrong mapping, if you dig a well in the wrong place, that's a lot of money burned. Okay. So first, our idea is actually a very simple one, trying to help the geophysicists to map this network of tunnels where there might be oil so that they may actually plan how to dig their wells and get the maximum amount of oil possible from under the ground. Okay. So this is a kind of image that we have. This is a seismic image, I believe, from the North Sea. It's a public data set, one of the very rare public seismic data sets. And to me, this is just noise. Okay, I don't know how to interpret this very well. Someone with geophysical knowledge might know, but here we can see some features like this big line here that's kind of a crack under the earth. These cracks are exactly what we are looking for. And it's surprisingly hard to actually find them in an automatic manner. Some of them are very, very small. These cracks are where the oil flows. If I can dig my well to accompany this kind of crack, usually I'll be able to get the oil more easily out of under the earth. So I need to find these in a semi-automatic manner. Okay, so I still need a geophysicist to interpret this. So this here, for instance, is what a geophysicist mapped as a possible location of an oil reservoir. So it's not a big pool of oil, it's kind of this. Okay. So we have, this is like the kind of thing that if you improve 1% the output of your oil wells, you get like hundreds of millions of dollars a year in profit. Okay, so every single percent counts. So the idea is that this is a lot of work. We need a lot of data to train. And as you can imagine, oil companies are not really big on sharing the data, either with the public or with each other, because even if it will help your overall goal, it's still kind of a very hard competition. One of the most profitable businesses in the world is a well-managed oil company. It's like literally getting money out of the ground. Okay, I'm not sure if that still holds. Okay, but it did like 6 years ago. And the idea is that we need to help the geophysicists to get that to make that correct interpretation, to help the people that will plan how to explore that. And that's a lot of manual work, a lot of data, a lot of noise. Oh. And there are a lot of works that try to tackle this. Most of them try to use a mix of synthetic data, which is a very simple model, and transfer learning for like to try to apply this to real world data sets. Problem is, seismic images from different places of the world are very different. Transfer learning is a very hit or miss in this case. And we have like recent models that are like huge transformer architectures that need a lot of data, that need a lot of training, a lot of labeled data, and this takes time. I'll skip the related work session here because we have like 2 minutes. So our idea was like put a very hard foot in the brakes and say, well, why can't we use simpler models like convolutional neural networks with self-attention again, and try to see how we can improve this, okay? And we use the same approach of using static data and transfer learning to try and make to have more data to generalize, train and then generalize to other types of data sets. And our input patches are like 44 pixels in the direction. And we, with the help of a geophysicist, we were able to train on the F3 block, that's a seismic block from the North Sea, and then generalize it to a block in the New Zealand basin. Okay, this is also publicly available. And our model, even as simple as it is, outperformed even the transformer-based models by okay, it's comparable, it's not a large margin. Here, these are the models published in like last year and last 2 years. The intersection of reunion of ours was slightly better, but we had a much better F1 score. And it's okay. And basically, even simpler models, given a clever application, can still outperform very large transformer-based architectures. We can use transfer learning, we can use synthetic data sets. And I'm sorry, I had to run a lot. These are some of the results we have from a geophysicist RL model, okay? And we found a lot of fractures and faults here. We can talk a little bit more in the poster session, I'm sorry. But this is basically, even older models can still outperform much sophisticated ones, given the correct tweaking. Okay. And thank you very much.
We have time for a couple of questions. Questions for presenter? Question? Any question?
I have one. So yeah, you were saying that it's very difficult for the humans to look at those cracks because
yes.
they can be very small.
Yes.
And has there been any type of work that tried to look at this from different perspectives, like for example, translating that into signal and analyzing signal, for example, and that would need to improve the results? Do you know anything that was in that line of that?
Well, that signal that we have here, this is I'm going to try and explain what I understood. Okay, this is actually a signal that is in the time domain. These are the layers of soil where a very powerful sound cannon was detonated, and then some very powerful and sensitive microphones very far away got this. This is like almost a sonar of the Earth. Okay, and this is mostly converted from time that it took, it's like a radar, back to depth. Some of the work, we are kind of limited, but because these kinds of data sets are very expensive to acquire. And usually, for some reason, our oil companies are kind of short-sighted in this, and they discard the time, the original raw data, because it's like terabytes upon terabytes of data. And then they keep these depth-only representation. This is kind of very low resolution to get some of the more important things. So we're kind of limited for resolution as well. But I'm not sure. Other than like spending a lot of money to get better data sets, I'm not sure if there is another work to try and improve this, okay? Yeah.
I was wondering, because, you said that, right now, what you do is predicting on a pixel level, the classification of each pixel, right?
Yes, region basically, yes.
So, has there been like, I mean, looking at from an outsider perspective, they look very sort of geometrically consistent, so I would think that fitting splines or, something around with graph prediction might work better in this case.
One of the works here is actually, I had to skip it, but one of the works here is actually a graph neural network for this. And one of the problems is that they still kind of not really solve the problem. We still have very little available annotated data, and these models are usually slightly more complex. So it's kind of hard to scale them as well. But yeah, it's a viable, once we solve the data availability problem and the computational problem, it's a very good alternative as well, yeah.
Next question.
Yes.
In this type of data, like the geometry of the acquisition actually matters a lot. Like the sources and the sensors are placed like according to a geometry, some distances and this kind of designs. Do you know like what type of geometry are you using? Are the sources regularly spaced or, and how does that affect, or do you think it would affect your model?
Well, I'm not really sure about distances, but what I know about the acquisition system is that basically a bunch of one chip with a really powerful sound cannon that's actually terrible for the environment because it kills everything in the area, everything. And kind of far away, they have a huge grid of microphones. I'm not sure about the size, but several kilometers away. And then when they detonate this cannon, the sound waves go under the earth and then they start reflecting because of the properties of the soil. But I'm not really sure. They have a huge grid of microphones, but I'm not really sure about size or about regularity in the sampling. I'm sorry, I don't.
For marine acquisition.
Yes, for marine acquisitions mostly, yes. I'm not sure about ground acquisitions. I think they use TNT for that, not sound cannons with literally explosions.
Okay, thank you. Thank you. Remember that if you have additional questions regarding this topic, you can find in the post session. Thank you. We will go with the last presentation of this oral block. Sorry, the second. Okay. Ramon, where is Ramon? Hello, Ramon. Well, for our second oral presentation, let me introduce Ramon from Mexico. Thank you, Ramon.
Hi, everyone. Well, our work is titled "The Myth of the Pyramid." I come from the south of Mexico, from the Mayan area, so we have a lot of pyramids there, and we always ask why they did that buildings in that form. Hopefully, we can figure out why. And in this work, we have found that design in a lot of convolutional networks. So we ask as well why this design is present in all those architectures. Yeah. So it is generally believed that a progressive increase in the number of kernels compensates for a possible loss of the representation caused by the spatial resolution reduction, as well as improves performance by keeping a constant number of operations in each layer. This pattern can be observed in a diverse set of models like BGG, ResNet, and MobileNet, and even models obtained for neural architecture search, such as NASNet, follows this principle. So it has been taken for granted that this design is optimal for all models and datasets, at least in the computer vision domain. To challenge that myth that the pyramidal distribution is of universal applicability, we evaluate a small set of predefined distribution that we call templates on several node datasets. These patterns are defined with very simple linear and piecewise linear functions, which enables designers to easily implement them on most of the existing CNN models. The patterns are not arbitrarily selected. They are inspired by designs found in previous works and by pruning automatic model discovery methods. Following the findings in the pyramid paper, we reduce a step change in all the patterns in our experiments. So we have found that this smoothness improves accuracy in almost all of our models. So our first approach to change the filters in an architecture was to keep the original filters in the resulting model, but redistribute them differently across the layers. Nevertheless, final models end up with different resource demands, and therefore making fair comparisons was really problematic. So we believe that using one metric is insufficient for impartial comparison. As examples, for processing the CIFAR datasets, our implementations of BGG and ResNet count an approximate number of parameters, 20 million versus 23 million. But the ResNet flops are more than 3 times BGG flops. To facilitate evaluations, we matched one metric well compared to the other. In particular, all models obtained from templates match the flops of the original model. And then we compare other metrics, such as accuracy parameters, memory footprint, or inference time. In this example, we show the final number of filters in each of layer of BGE model modified with templates. We see the increasing A template differs from the original in the smoothness of the change. The uniform distribution set all filters to 153. In all cases, the minimum number of filters in a layer for the whole model matches the minimum number of the original base designs, 64 in this case. This prevents a model suffer from representational power loss cost for the bottleneck effect. Experimental results show improvements in accuracy and resource consumption for BGE and ResNet architectures in all of the 6 datasets evaluated. In some cases, reaching higher accuracy with up to 65% less parameters. These results show the positive effect of different distributions despite the template patterns were selected following simplicity and diversity, but not focus on efficiency. We know that both MobileNet and MNASNet perform best in tiny ImageNet datasets. We believe this is because tiny ImageNet is strongly related to ImageNet, and designs have been optimized to the latter. However, template A is still competitive with reductions of 1.5 points in accuracy, but savings up to 49% in parameters. In the audio classification domain, by using templates on ResNet, we got improvements in accuracy between 1 and 2% over the base model. We highlight that template C in GT obtaining a similar accuracy with only 14% of the original parameters. We compared the base model in the NASBench dataset. It contains more than 400,000 automatically discovered CNN networks evaluated on CIFAR-10. The search space of NASBench is restricted to this pyramidal distribution of filters. Template C obtains a higher accuracy than the best performing model with 1/3 of the parameters. Yeah, of course, we are not aiming for templates to outperform any neural architecture search method. We state that combining templates with search methods can deliver further improvements to final CNN models at a very low cost. In all the experiments performing this work, the templates use similar flops than the original architecture. So in summary, this work challenged the pyramidal filter distribution present in many neural networks by using a set of varied templates that modify the original filter distribution. For almost all case tested, template models delivers best performance and reduces resources with advantages that go beyond the domain of image classification. The experiments indicate that for each model tested, there is no particular distribution of filters that guarantees the best accuracy on all tasks. This means results of automatically searching for the number of filters in a small dataset, such as CIFAR, should be carefully extrapolated to other datasets. In the opposite direction, models with distributions that work well on extensive datasets should be changed with templates, for example, to perform efficiently on different domains. That's it. Thank you.
Time for a couple of questions. You have questions? Yeah, go ahead.
I was wondering why you didn't consider pruning network application.
Well, the main difference is that we just propose to open the search space for neural designs. Pruning networks have let's say a cost of finding what is the best nodes to prune, and here we just adjust the filters, and that's it. You train the model, so there are no hidden costs.
Yeah. Next question.
I see that you mainly focus your work on evolutionary networks, right? How do you transfer your learnings into the vision transformers? If there is any way to apply it?
Yeah, well, the transformers, starting they don't use the pyramidal design. They use uniform design. So I haven't worked on them. I couldn't say that. Yeah, but if they have a number of modules, not filters really, but modules, you could try just to change the number of models in each step.
So in theory, we should be able to find similar kind of templates, right? If there is a transformer architecture.
Yeah, actually, what we wanted is just to open the search for new designs, not to propose a technique for finding the best templates.
Thank you. For time, we will go with the next author, and can find you in the poster session for more questions. Thank you.
Thank you.
Esto es un PowerPoint. No, PDF. No. Uy, no. No, ese es izquierda, ese está mal. Déjame ya lo. Está en el derecho. En la carpeta, es un papel. Ahí donde central, la material. Presentation, recording slides. Pérez, ¿no? Sí, Pérez. Descargar. Tener que meter no funciona. Ok. Descargar. Acá. No lo abras ahí, sino descargarlo directamente desde el Drive. Descargar. Acá, ¿qué tú quieres que lo descargue acá? Como, no, otro. Ah, ok, no lo abre. Ahí, eso. Ya. Ya está. Arriba a la derecha está. Eso es de ahí.
Okay, for our last talk for this oral session, let me introduce Robert Rueda, one of our chairs of this workshop. Welcome, Robert.
Okay, so morning everyone. Thanks for stopping by or staying. So the last is for the better, so the better is for the last. So let's hope for the best. First of all, I have to say that this work was jointly done with my student, Fabian Perez. Super smart guy looking for internships. So if you like this job or this work, please reach out. He's actually currently in Colombia and he's an undergrad student. So let's show. So our work is called Beyond Appearances, so material segmentation with embedded spectral information from RGB imagery. So first of all, I want to introduce like what material segmentation is. So we can see here like most of work on segmentation is mostly on semantic segmentation. So we have like a motorbike there and maybe some like background information, but we are interested on material labels. So here we have like paint and concrete, some asphalt or plastic or different classes. This has been used recently a lot, and one of the goals is to have like a richer segmentation map and also dense map, but a richer segmentation map that can actually help us like not just tree and cars, but we have also like actually have leaves and trunk and like different classes in here. It will help like different application, like in autonomous driving, you can actually try to recognize like what kind of road. So we have like concrete or segment, or we have like any different materials, open road. So that's one of the useful applications. Also for realism, now rendering and all these different like trying to create like synthetic scenarios. You can be like more basically have more realism on like those scenarios. And also for navigation, like if you have a robot or something similar, like you want to teach the robot how to interact with objects. So if this is wood or this is plastic or this is like metal, how do you like hold things? So this is different. So that's why it's important to know like what kind of material is you're interacting with. So also like a side effect is like a depth estimation is also useful for navigation, not just the material. So that's why we delve on trying to this latest network from, I guess it's Apple, that they train with a super big data set and just like a monocular depth estimation network, you can have a like depth map, super nice depth map and with point clouds. But for this work, we actually rely on like off-the-shelf RGB data. So we want to democratize somehow the need of how can we do material segmentation, but with like off-the-shelf devices. So we will show a cool demo at the end of the talk. So for now, the general approach of material segmentation is relying on RGB images. However, we have a metamerism. For those that are not familiar with metamerism, like different materials can look the same to your naked eye. So for instance, here you have checkerboard, but these are different materials like in the shoe or in a belt. So how do you differentiate these different patterns, although it's the same pattern to your naked eye? Also, a more challenging scenario when you have plastics. So all these are same material on the right, but it's just like different colors. So maybe you can be fooled with the different colors or shapes, but the material is important in this to basically check like, yeah, these are exactly the same material or same class of material. So with this in mind, one of the key components and actually what we exploit and my experience is about spectral information. So spectral information is some sort of a fingerprint of materials on nature. So you can see that we have different materials here, just for example, 4. So brick, stone, wood, and marble, although they are like different stones or kind of different materials, you can see like they behave differently when you just have not just 3 points like RGB image, you have a red, green, and blue channel, but you have a collection or spectral signature of that. So how can we actually measure spectral information such that you can incorporate that to your like device? So based on that, we actually propose this architecture. The RGBD image pair is the input to encoder-decoder architecture, which basically is trained end-to-end to have some sort of a spectral feature. But this feature enter to our proposed model, the spectral feature mapper, which basically uses a spectral data set to basically do some sort of attention mechanism for basically see these output features actually correspond to some like consistent spectral mapping. But one of the things that I want to stress is like spectral information is just required for training. So we can do this offline and then like release our stuff, and we will just rely on RGB image for like evaluation period. So this output of SFM will go to a softmax, and then we will have this segmentation map. We use this different like a composite of segmentation and reconstruction loss functions, but I want to stress out like we rely a little bit more on the, we weighted more the segmentation loss. Delving a little bit more on the SFM module, let's assume we just take one of these pixels. So a pixel of this cube is actually a spectral signature. The SFM module, in short, will compute the cosine similarity between the actual signature and what's learned. And depending on that, we will basically have this like negative sign on the cosine similarity, because closer to zero means more like similarity. So that's why we have the negative in there, such that after the logics go through the softmax, so we have like a segmentation map, like a binary segmentation map for each one of the classes for all the height and weight of the image. So yeah, that's the proposed framework. So as I said, you will have just a RGB or even RGB-D sensor. The measurement will go to the encoder decoder, and the training SFM layer module that will be available will basically depend on this material segmentation map. Plus, given that we have the depth image, we can sort of do the 3D like point cloud, and yeah, that's the goal. So just to show, sorry, I'm running out of time. For the segmentation loss, we use the focal loss. For reconstruction, the NSE. These are the actual training parameters if you want to see more about those. And these were like results with state of the art. So this paper in 11 use the UNet or the FCN, and our results are pretty much better. So we can discuss more details in the poster session if you want, but these are just special reconstructions of that. We also tested with real world experiments. So we took our iPads and went outside of our building and acquired some data. We used the ARKit SDK from Apple to access the data. So it's very somehow difficult to access the data, like raw data. So we actually had to do it with the ARKit and try to basically know this 32 by 32 point cloud data from the iPad. So we went outside of our building. These are just like examples of that. So the data set that we use is just for packets. So that's why we are constrained somehow to packets. So I mean, like we have some like bricks with some trees or some different classes. And these are like real data. We have RGBD, and these are the segmentation and the point cloud result with that. So just takeaways, the spectral feature mapper is the model we propose. So it basically enhances the encoder decoder architecture by embedding spectral characteristics into this work. We achieved like great results with just RGB methods, and based on that state of the art that we know as for our knowledge, we obtained like great results, and we validated that with a like off-the-shelf iPad Pro. So it's available. Please check our codes. And this on the left is our soccer club in Bucaramanga. We just won the first star, so we are super happy with that. So yeah, thank you. Yes, that's question.
Okay, we have time for 2 questions. This is the question. Okay, go ahead, Jose.
How is this different from the, for example, SAM, the segment anything model?
Yeah, I guess they are still constrained. Please correct me if I'm wrong. I think they are still constrained to semantics, not material.
I'm not really sure because they released this SAM for 3D or something like that. But
Yeah, they want to
I'm not
segment
sure.
anything. So yeah, I am aware of the work. We are aware of the work, sorry. But yeah, I guess what makes us different is like, let's move to materials. Let's try to move this new like venue, because I guess semantic is already saturated. And it's very, I mean, we don't have like clusters in Google or this big company. I guess we are screwed. So that's why we are moving to these different like options. Also, maybe instead of spectral information, we are exploring like a polarization or maybe other different domains, such that we can have a chance in this world.
But sorry,
Yeah.
so, do you think it is possible to do some kind of like a fine tuning on the, for example, SAM, and then just compare the results?
Yes, that's actually our current work. I cannot disclose more, but yeah, the goal is to like do some sort of pre-training on that, and then just do like
just
fine tuning on
like
this.
focus on the materials.
I agree. Yeah, completely agree.
Thank you. Last question, there?
Yes, thank you for the presentation. I think it was very interesting about like the explainability part with the design similarity.
Yep.
I like that.
Okay, thanks.
Maybe you're already working on this, but have you considered using like multi-views as input, not just like one RGB and B? It's like a multi-views.
Yes, actually, we started with that goal. I mean, I'm being honest here. We started with that goal. First problem was like processing time. Like when you have like multiple views, like a video, RGB video, it's great. We can do better triangulation. We can do actual 3D point clouds. Here is like a 2.5D, as we know. And we are actually considering, but we are lacking resources. I'm looking for nice people to lend me some DPUs. So yeah, but we are pursuing that. I mean, that's the actual, I would say, final goal of this is like.
It would be very cool to have like this kind of materials there.
Mhm.
So you could use there, but with the multi-views, and then you render the 3D materials.
Yeah, you're reading my mind. Yeah, that's right. That's right. That's the way to go. Yeah.
Okay.
Thank you.